Kia ora, Year 12 and 13. This is a revision question from a Pure 3 paper from November 2015. So Havisha asked me about the first part of this question and I really liked all of it, so I'm going to video it for you. The first one's differentiation. So we're given the equation of a curve, and it's this curve here, and we're told that x is between 0 and pi on 2. First we have to differentiate it and show that it can be written in this form. And a and b are constants, so we have to find them. And then we have a couple of follow-up questions. Then the second question here is going to be a remainder theorem and factor theorem question. So let's start on question 5. So the function is y is equal to e to the negative 2x tan x. So it's a very easy product rule question. So dy by dx is equal to e to the negative 2x times the derivative of this, which is sec squared x, plus negative 2 e to the negative 2x times tan x. Now we're asked to show that it can fit this form. So notice here we've got a quadratic in tan. So we've got a constant, a tan x term, and a tan squared x term. Down here we've got a sec squared term. So what that should make you think of is the Pythagoras identity. So the first version of that you learned was sine squared plus cos squared equals 1. Just dividing everything through by cosine squared gets me what I want. So tan squared x plus 1 is equal to sec squared x. Most of you will know this one off by heart anyway. So if we substitute this in here, that's going to be a good way to generate the quadratic in tan. So let's do that now. So dy by dx is equal to e to the negative 2x times tan squared x plus 1. And then from here, we're going to have minus 2 tan x. So this is a perfect square in tan. This is e to the, oops, turn off the shape thing. Sorry about that. Okay, we've got e to the negative 2x times tan x minus 1 squared. But the form we're asked to give it in is with the constant first. So we can rewrite it like this, negative 1 plus tan x all squared. And that gives me a is equal to negative 1 and b is equal to 1. Let's just go up and check what we've got to do with it next. Okay, so now that was worth 5 marks. We've got to explain why the gradient of the curve is never negative, and then we have to find the value of x that minimizes the gradient. So dy by dx is equal to e to the negative 2x times tan x minus 1 all squared, and e to the negative 2x is greater than 0. Remember that this is the curve of e to the x, this is e to the negative x, and e to the negative 2x is just a vertical stretch on that. So it's more like that. Whichever way you look at it, it's strictly positive. Okay, same thing in here. It doesn't matter what value this takes on. This is going to be greater than or equal to 0 because it's a squared number. So when can we minimize this function? Well, it'll be when it equals 0. So dy by dx equals 0 when this term is equal to 0, because this one can't be. So when tan x equals 1, and so x is going to equal pi on 4. Remember that I'm just working with x values between 0 and pi on 2, so there's only one solution to that. So that's the first question done. Okay, so the derivative is, the gradient is lowest when x is pi on 4. Okay, let's take a look at the next one. We've got a polynomial, and it's got 2 missing coefficients, and it's denoted by p of x. And we're told that x plus 1 is a factor of p of x, and that when p of x is divided by this, the remainder is 1. So to find a and b, we're going to use the factor theorem, and we're going to use the remainder theorem. Then we're going to follow up by factorising p of x completely. So let's just start by writing out what p of x is. So p of x is 8x cubed plus ax squared plus bx minus 1, and x plus 1 is a factor. So p of negative 1 is equal to 0 by the factor theorem. P of negative 1 is equal to negative 8 plus a minus b minus 1, which equals 0. That gives us a take away b is equal to 9. Now we're told that when we divide by 2x plus 1, we're left with a remainder of, let's see, of 1. I think I'll just have to go back to the question to check that. Hang on. Yep, so when we divide by this, the remainder is 1. So what we're saying is we need to solve 2x plus 1 equals 0 to find the value to put into my remainder theorem. Most of you will be doing that easily, but that's just a quick memory jog. If you're not confident with that, you need to go back to delta, to the very early stuff on remainder theorem. So this gives me x is equal to negative a half. And because we know the remainder is 1, by the remainder theorem, it's telling us that when we evaluate the polynomial at this x value, the polynomial will have a value of 1. So p of negative a half is equal to 1. Substituting that in gives me 8 times this cubed, which is negative 1/8, plus a times negative a half squared, plus b times negative a half minus 1, and that needs to equal 1. Right, simplifying here gives me negative 1 plus a quarter a minus a half b, take away 1, equals 1. So we've got two simultaneous equations coming. A quarter a minus a half b is equal to 3. Multiplying through by 4 to clear out the fractions will give me a minus 2b is equal to 12. So we've got this one, but we've also got our first one, which is a minus b is equal to 9. So we're going to solve those simultaneously. You can either use substitution or elimination. I usually like elimination, but in this case we can easily say that b is equal to a minus 9. So I know most of you are going to use this method, so I'll do it too. So a minus 2 into a minus 9 is equal to 12. That gives me negative a plus 18, plus 18 is 12. Negative a is equal to negative 6, a equals 6, and b must equal negative 3. Okay, so we've substituted this a value back into here. Right, let's have a look at where we're up to. I think we're just about finished the first part. Right, we've found a and b, and now we have to factorise p of x completely. But we've already been told one of the factors, and we've got a cubic, so it's not going to be too bad. So what's p of x? Well, p of x is 8x cubed plus 6x squared minus 3x minus 1. And that equals x plus 1. And now I'm just going to match some terms to start getting out the quadratic part. So 8x cubed must be 8x squared. Let's leave the x term for the next line of working. And here I must have minus 1. Right, now I can match up pretty quickly just by inspection. If I want to generate plus 6x squared here, I'm going to have plus 8x squared here, so this must be minus 2x squared here. We're not quite finished yet, so we can have 8x squared minus 2x minus 1, and we can just check that we get the minus 3x that we want. So here we've got take away 2x there, and then take away another x here. So that all works. The last thing we've got to do is to factorise that quadratic, and we should be able to do that by inspection. The reason it's so easy to do by inspection is because I've got a minus 1 here. I should at this level be thinking that 4 2's are 8, might be going to help me generate that middle term there. So let's give it a go, and if we have to, we can go and do, I don't know, quadratic formula or something, or grouping, but it turns out that we don't. We can have 4x here and 2x here. We need to have a plus 1 and a minus 1, so we're going to put the plus 1 here and the minus 1 here. Now let's see if that works. 8x squared plus 2x minus 4x minus 1. So we're done. Okay, so we've factorized it, and we could now do the 3 solutions, but it hasn't asked us for that. So that question is finished. So there you go, some good, really basic revision on factor and remainder theorem. I think this is about as straightforward a question as you're going to find. Both of these questions are good for level 3 NCEA as well, obviously not in the same paper. So the second question is good for the complex numbers paper, and the first one for differentiation.